the number of this room?
H001B.
Oh, B.
Yeah, there's a B, that's A in there.
What happens when I take this wall down there? Is it
C.
Yeah.
Combined.
Maybe okay, yeah, we're rolling.
Right, I'm excited.
Hi guys, today I'm going to talk about absorption and absorbers. So, moving on. First, definition of bass traps, which is the second part of my presentation. Moving on to a bit. Bass traps are basically acoustic absorbers which capture low frequency sounds. They're used to soundproof rooms, for example, in a recording studio. Bass traps provide an easy way to control and limit low frequency noise within a set environment, and they function by turning sound energy in a room's air volume into minute amounts of heat through friction. First we're going to look at a bit of theory behind it. Sound is obviously transmitted through gases, liquids and plasma as longitudinal waves as opposed to transverse waves. Longitudinal sound waves are waves of alternating pressure deviations from equilibrium pressure, causing local regions of compression and rarefaction, as you see there. So as the air pressure varies and is changed, it forms a wavelength. They're characterised by the numeric property of wave, which is frequency, wavelength, period, amplitude, intensity, speed and direction. Speed and direction are often combined to make velocity. Whenever the pitch of a sound wave is affected by some kind of change, the distance between the sound wave maxima also changes, resulting in a change of frequency. When the loudness of a sound wave changes, so does the amount of compression in air of the wave that's travelling through it, which is what gives you amplitude. The speed of sound obviously depends on the medium through which the waves are passing. For the purposes of controlling frequency levels through air at room temperature, the speed and velocity of sound can be calculated like that. Velocity, which is V, equals 20.1 times by the square root of 273 plus whatever the temperature of the air is. Based on this formula, there's obviously a table here cataloguing the velocity, speed of sound through various media. And it's in meters per second, so 5,189 meters per second is steel and so forth. And air, usually it's 20 or 21 degrees C is the room temperature we take, so that's 344 meters per second for air. The absorption of a room can be calculated by multiplying the surface area, which is S, by the average absorption coefficient, which is the alpha. Thus, Sable's equation for calculating reverb time, which a few people have spoken about today, can be applied like that. The RT60 time equals 0.61 V times V divided by SA. And from this we can calculate the absorption coefficient. And obviously here we've got a table showing different absorption coefficients for different materials you can use to soundproof a room to make absorbers and stuff like that. Right, onto absorption. Absorption in this instance means the absorption of sound waves by a material. It's the missing piece of the equation that I showed just a second ago when comparing the initial energy of a sound wave meeting a surface with the energy reflected by the surface. So obviously you've got the incident noise, which is the source of the sound, like me going like that, hits the wall, some is reflected and some is transmitted through, and that's just a panel absorber. Absorption is a property of the material that converts the kinetic energy of a sound wave into heat energy. Material that absorbs sound waves pretty much doesn't reflect them. As you can see, it reflects some, but not as much. The more the material absorbs sound, the less it reflects. The absorption of a given material is dependent on a number of factors, including the frequency of the wave hitting the material, and the size, shape, and location within the room of the absorbal of the material itself. And also the method by which it's mounted is also a factor, whether it's in the ground, whether it's mounted like this one with a plywood in front of it, or just as is. And porous materials make the best sound absorbers. For example, mineral wool, glass wool, and micro-perforated plates are often used. Right, so we talk about bass traps. There's generally two types of bass traps. The resonating absorbers are likely to only absorb a small amount of frequencies, and this is called narrowband action, and they absorb, like with bass traps, very low frequencies. Porous absorbers are likely to absorb a more full range of frequencies right across the audible spectrum through to the inaudible. It's called broadband action. Both types can be changed to absorb more or less a wide range of frequencies. They can be tuned, and both are effective, but as a rule the porous traps are considered to be more practical in their use as they apply to a wide range of environments, whereas the resonating traps require tuning, as I said before. So the more commercially viable bass traps are of the porous variety. Resonating traps are based on membrane-like diaphragmatic elements which are left free to vibrate in sympathy with the room's air when the sound occurs. So if you take, for example, the Helmholtz resonators here, that's basically just empty air inside of there, and there's a hole in the top